In our last video, we covered binary search and saw how we can repeatedly chop our search space in half to turn slow, linear scans into logarithmic O of log n lookup speeds. It is an insane optimization when your data is stored and sitting in a flat array, but it relies on one major assumption. Your data is flat, indexable, and linear. But what happens when your data isn't a flat list? What happens when your problem naturally breaks down into nested structures, dynamic subproblems, or self-referential operations? Say you're parsing a massive JSON payload with unknown levels of nesting, traversing a file system directory tree, or resolving package dependencies inside npm or yarn. If you try to write traditional iterative for or while loops to handle dynamic depth, you fall right into a maintenance nightmare. You end up writing ugly, fragile, nested loops or manually juggling complex dynamic stacks just to keep track of where you are. This is where we need a complete shift in strategy. Today, we are starting with recursion and DFS. Starting with recursion, instead of forcing a problem into a flat loop, recursion lets a function call itself on a smaller chunk of the exact same problem until it reaches an answer. So simple, it doesn't need to calculate anything. Now, recursion gets a bad reputation for being abstract or confusing, but in real world production engineering, it's everywhere. In plain terms, recursion is when a function calls itself to solve a smaller piece of the problem until it reaches an answer it already knows. So, whenever you deal with nested data like folders inside folders or menus with submenus, using regular for loops gets messy because you don't know how deep the structure goes. Recursion simplifies this by letting the computer automatically track how deep you are using the call stack. It is the system's memory for keeping track of function calls. Every recursive function needs two main parts. The base case, it is the stopping condition. It tells the function, stop calling yourself and return a value now. Without this, your program gets stuck in an infinite loop and crashes with a stack overflow. Now, the second one is the recursive step, the part where the function calls itself on a smaller version of the input data. Even your operating system relies on this. When you run this command in your terminal to delete a folder, the OS doesn't just sweep through the single flat list. It hits a directory, opens it, calls the deletion routine recursively on every subfolder inside it, hits the raw files at the very bottom, and pops back up the stack to safely remove the empty directories. To really see how the recursion changes the way we write the code, let us look at a quick example of calculating the factorial of a number. Now, if you remember from maths class, the factorial of 5, written as 5 exclamation mark, is just 5 times 4 times 3 times 2 times 1, which is 120. Now, if you solve this problem the normal iterative way, you'd use a standard for loop. You initialize the variable to 1, loop through every number up to n, multiply them step by step, and manually keep track of the result. Now, it does get the job done, but you're manually managing state variables like result and I throughout the loop. Now, let us look at the recursive way. Instead of building up from 1 to n, you ask a different question. What is n actually made of? Well, 5 factorial is really just 5 times 4 and 4 factorial is just 4 times 3 factorial. In other words, the factorial of a number is just that number times the factorial of the number right below it. Here's how that looks in code. Look at how clean that is. You don't need for loops and you don't need to manually update a result variable. First, we check our exit condition, that is this. This is the base case. When n drops down to 1 or 0, the function stops making additional function calls and returns the concrete value of 1. This stops the recursion and prevents a stack overflow. Next is the recursive step. Instead of updating a loop variable, the function multiplies n by the result of calling itself on a smaller subproblem. Let us trace what happens on the call stack if you call this function. Let's trace what happens on the call stack if you call this function with the input 3. So when the function runs, first of all it checks if 3 is less than equal to 1. It's false. So it pauses execution, waiting to evaluate 3 into the function itself, but now the input is 3 minus 1, that is 2. And it pushes a new frame for the function with the input 2 onto the call stack. Now, when the function runs with the input 2, it checks if 2 is less than 1. It is not. So it pauses execution, waiting to evaluate 2 into the function now with the input of 1, because 2 minus 1 is 1. So it pushes a new frame for the function with the input 1 onto the call stack. Now again, it checks if 1 is less than or equal to 1. It is true. It hits the base case and returns 1. Now finally unwinding the stack, the function with the input 2 receives 1 and completes the pending operation, that is 2 times 1, that is 2, and returns 2 back up to the function with the input 3. Now the function with the input 3 receives 2 and completes its pending operation, that is 3 times 2, that is 6, and returns the final result 6. So instead of writing loop logic to manage state, you defined the core mathematical rule and let the call stack handle the execution order for you. Now that you have recursion down, transitioning to depth first search or DFS is super straightforward. In fact, DFS isn't some completely new concept, it is literally just recursion applied to a tree or a graph structure. While regular recursion breaks a general problem into smaller subproblems, DFS uses this exact same recursive mechanism to navigate through linked data nodes. The core idea behind depth first search is right in the name. Go as deep as possible down one single branch before backtracking and trying another one. Think about a maze. If you hit an intersection, you don't explore every path simultaneously. You pick one path, walk down it until you hit a dead end, step back to the last decision point, and try the next path. The exact strategy is DFS. You will encounter DFS in algorithms and system design whenever you need to explore every possible path or inspect nested relationships. Look for keywords in project specs like tree traversal, connected components, pathfinding, detect cycles, or nested dependencies. When you perform DFS on a tree or a graph, you follow a simple recursive pattern. Visit the current node, that is, perform whatever operation or check you need to on the node you are currently sitting on. Then, base case or the shopping condition. If the node is null, is a leaf node with no children or matches your target search value, you stop and return. If you're working on a graph that has cycles, that is loops, your base case also checks if you have already visited that node to prevent infinite loops. Recursive step. Loop all over adjacent neighbors or child nodes and call DFS on each one recursively. Because recursion lies on the call stack, the computer automatically remembers every parent node you came from. When a recursive call reaches a dead end, that call finishes, pops off the stack, and seamlessly backtracks to the parent node so you can explore the next child branch. Imagine you have a binary tree, a root node with a left child and a right child, and you want to find the maximum depth, that is height, of the tree. The goal is simple: find the longest path from the root node down to the deepest leaf node. Let us walk through how this runs under the hood. First, we check our base case. If we hit a node that doesn't exist, like moving past a leaf node at the bottom, we stop. It contributes zero depth, finishes that function call, and pops it off the stack. Next, we hit the recursive step. We make two recursive calls, and this is where DFS kicks in. The program pauses execution on the current node and dives all the way down to the left subtree until it hits a null base case. Finally, we hit the combination step. Once both subtrees return their heights, we take this function to pick whichever side went deeper. And we add 1 to account for the current node itself. Then we return that result back up to the parent call. Now to trace this step by step, imagine a root node A which has a left child B and no right child. You call this function for A. Node A is valid, so it pauses and calls this function for B on its left side. Node B is also valid, so it pauses and checks if its left child, which is null. Now this function with null triggers the base case and instantly returns 0 back to B. Node B then checks its right child, which is also null, now returning 0. Node B then combines those results and returns 1 back up to A. Now root A resumes. Its left side returned 1. It checks its right side, which is null, so that returns 0. Root A computes this, which equals to 2. The function finishes unwinding the call stack and returns the final tree depth, that is 2. Notice what just happened here. You didn't have to write nested loops, keep track of dynamic arrays, or manually push and pop state frames. The system's call stack handled the entire traversal, memory management, and backtracking for you. Whenever you're tackling any recursion or DFS problem, the secret isn't trying to trace every single node in your head. That's how you get overwhelmed. Instead, focus entirely on what a single node needs to do. Just ask yourself 3 simple questions. Number 1, what is my base case? Like, when should this node stop and return a value immediately? Number 2, what do I need from my children? Like, what subproblem result does this node expect back from its left and right calls? Number 3, how do I combine those results? Like, how does this node aggregate its children's answers and pass the updated result back to its parent? Once you define those 3 rules for a single generic node, the call stack takes care of the rest across the entire structure, whether your tree has 10 nodes or 10 million. And with recursion and DFS lockdown, you now have the full core foundation for handling data structures and algorithms. This completes all of our core concept breakdowns. From here on out, we are shifting gears into hands-on problem solving. In the upcoming videos, we are going to take these exact patterns and deploy them against real-world interview problems. We'll break down how to instantly spot which pattern to use, how to write the code cleanly under pressure, and how to optimize your time and space complexity on the fly. As always, the resources are in the description below. I'll see you in the next one.